Picture the space between the stars. Cold, silent, infinite nothingness. A perfect vacuum stretching across the universe. That image feels right. It feels obvious. It is also completely wrong. What we call empty space is not empty. Not even close. Inside every cubic centimeter of so-called nothing, particles flicker in and out of existence billions of times each second. Invisible fields press against your skin right now. The void hums with energy older than the stars. Before we drift deeper, softly like this video and subscribe. It helps these quiet journeys reach more curious minds. And tell me in the comments, where are you resting tonight? And what hour glows on your clock? Begin with something simple. Hold out your hand in front of you and look at the air between your fingers. There is nothing there, or so it seems. The space feels like a gap, a pause in the world, a quiet absence waiting to be filled by something more interesting. This intuition is not foolish. It is one of the oldest and most natural feelings a human mind can have. For as long as there have been people who looked up at the sky and wondered, there have been people who assumed that the dark gaps between the stars must be made of nothing at all. This feeling is so deep that it shaped the way entire civilizations spoke about the world. Long before telescopes, long before laboratories, long before the word vacuum was even written down in any language, humans were already debating what nothing might be. And the strangest part of that long story is that the question itself, the simple question of whether nothing can exist, turned out to be one of the most difficult ideas ever placed before the human mind. Stay with me for a moment, because the journey we are taking tonight begins with people who lived more than 2,000 years ago, and it ends inside the silent trembling of every cell in your body. But to understand why the void is not what it seems, we have to begin where the story began. We have to begin with the first people who tried to imagine nothing and discovered that nothing was harder to imagine than they expected. In the gardens of ancient Greece, a philosopher named Parmenides walked among olive trees and arrived at a conclusion that puzzled everyone who heard it. He believed that nothing could not exist. Not in the casual way we use the word today, but in a strict, almost mathematical sense. To speak of nothing, he argued, was already to speak of something. The moment you named it, you gave it a kind of being. The moment you imagined it, you filled it with thought. True nothingness, he believed, could never be reached, never be measured, never be touched, because the very act of pointing at it would already make it into a thing. His students carried that idea forward like a torch through the centuries, and yet not everyone agreed. Another philosopher, Democritus, looked at the world and saw something different. He imagined that everything around him, every leaf, every stone, every breath of wind, was made of tiny, indivisible pieces moving through empty space. He called those pieces atoms, and he insisted that without empty space between them, those atoms could never move at all. For Democritus, the void was not only possible, it was necessary. Without nothing, there could be no something. Without emptiness, there could be no motion. These two ideas, opposite and irreconcilable, began the longest argument in the history of human thought. Is the void real, or is it impossible? Is empty space the canvas on which everything else is painted? Or is it a kind of illusion that the mind invents because it cannot bear to look at a universe full to the brim? For centuries, this question lived in books and lecture halls. Aristotle, the great organizer of ancient knowledge, took the side of Parmenides. He declared that nature abhors a vacuum. That phrase, repeated in classrooms for nearly 2,000 years, became one of the most quoted sentences in all of natural philosophy. The idea was that the world itself refuses emptiness. If you try to make a void, the surrounding matter will rush in to fill it. Air, water, anything nearby will press inward to prevent nothingness from forming. The universe, in this view, is a single continuous fabric, woven so tightly that not a single thread of true emptiness can ever appear. And for a very long time, this seemed to match what people observed. When you drink water through a straw, the water rises. When you pull the plunger on a syringe, fluid follows. When you pump air out of a chamber, the walls feel pressure pulling inward. Everywhere you looked, the world seemed to confirm that nothing did not want to exist. But notice something gentle here. Even in those early centuries, when the idea of a vacuum seemed impossible, people kept testing it. They kept poking at the edges of the question. They could not let it go. Because somewhere deep inside the human mind, there is a stubborn need to know what lies behind the surface of things. And the question of nothingness is the deepest surface of all. The slow centuries passed. Empires rose and fell. The libraries of Alexandria burned and were rebuilt and burned again. Through it all, the question of the void waited quietly in the margins of philosophy. And then, in the 17th century, something began to change. The change did not come from a philosopher arguing in a garden. It came from a young Italian student of Galileo who had been thinking about water pumps. His name was Evangelista Torricelli, and he had noticed something strange. Italian engineers had been trying to build pumps that could lift water more than about 10 meters high. No matter how powerful the pump, the water simply refused to rise any further. Above that height, the column of water would break, and a mysterious empty space would appear at the top of the pipe. For centuries, this had been treated as an annoying engineering problem. Torricelli looked at it and saw something else. He saw a window into a question that had been closed for 2,000 years. He filled a long glass tube with mercury, sealed one end, and turned it upside down into a dish of more mercury. The mercury in the tube fell, but not all the way. It settled at a certain height, leaving a gap at the top of the tube. That gap was the heart of the experiment. Torricelli stared at it and realized something that no philosopher had been able to demonstrate before. The space at the top of his tube was not filled with air. It could not be. The tube had been sealed. Nothing could enter. Yet something was clearly there, or rather, not there, holding the column of mercury in place. He had created what he believed to be a vacuum, a real, physical, measurable vacuum sitting on a table in front of him. It is hard, from where we sit now, to imagine the shock of that moment. For 2,000 years, the wisest minds in the world had insisted that such a thing was impossible. And here was a young man with a glass tube and a dish of mercury showing that it could be done. The vacuum had stepped out of philosophy and into the laboratory. The void had a measurable shape. News of his experiment spread across Europe like a quiet fire. In Germany, a man named Otto von Guericke heard about it and decided to take the idea further. He was the mayor of the city of Magdeburg, and he had a flair for the dramatic. He built the first air pump, a strange contraption of leather seals and metal cylinders, and he used it to suck the air out of two large copper hemispheres held tightly together. Then, in front of a crowd, he ordered teams of horses to be tied to each hemisphere and made to pull in opposite directions. The horses strained. The crowd held its breath. The hemispheres did not separate. The pressure of the surrounding air, pressing inward on the evacuated sphere, held the two halves together with a force that no team of animals could overcome. It was a public spectacle, but it was also a revelation. The void was not a theoretical idea anymore. It was a force. It could hold metal together. It could resist horses. It could be created, measured, and shown to a crowd of astonished spectators. And then, in England, a quieter and more careful man took up the work. His name was Robert Boyle. He was wealthy, patient, and obsessed with experimentation. He commissioned a new and improved air pump from a young assistant named Robert Hooke, and together they began a series of experiments that would change the shape of science forever. Boyle placed objects inside the glass chamber of his pump, sealed it, and slowly drew the air out. And one by one, he watched what happened to the world inside that shrinking atmosphere. Imagine the scene with me. A wooden laboratory table in 17th century London, a glass chamber on top of it, shining in the candlelight. Boyle leans forward. He places a small bell inside the chamber, suspended by a thin thread. He seals the chamber and begins to pump. As the air thins, he rings the bell from the outside using a magnet. At first, the bell rings, as expected, the sound clear and bright. But as more and more air is drawn out, the sound begins to fade, not gradually in the way distance softens noise. It fades in a stranger way, as if the world itself is forgetting how to carry the sound. By the time the chamber is nearly empty, the bell still moves, still strikes its clapper, but no sound reaches Boyle's ear at all. He can see the motion, he cannot hear the noise. Sound, he realizes, needs something to travel through. Without air, the bell is silent. Picture the wonder of that moment. A grown man, surrounded by books and notebooks and candles, watching a ringing bell that makes no sound, watching a hammer strike metal in perfect silence. For the first time in human history, someone had created a small region of space in which sound itself could not exist. He went further. He placed a small candle inside the chamber and pumped the air out. The flame burned brightly at first, then began to flicker, then to dim, and finally, gently, to die. Not blown out, not extinguished by water, simply unable to continue, because fire too needs something to feed on, and that something had been removed. He placed small animals inside and recorded with the careful, sometimes painful honesty of an early scientist that without air, life itself could not continue. He watched insects slow, then stop. He watched birds struggle, then still. These were not casual observations. They were the first physical proof that the air around us is not nothing, it is something. Something we breathe, something that carries sound, something that sustains flame and feeds life. And once you removed it, you were left with what seemed at last to be true emptiness. To Boyle, and to the scientists who followed him, this looked like a triumph. 2,000 years of philosophical argument had been answered with a glass chamber and a brass pump. The vacuum was real. It could be made. It could be measured. The candle that no longer burned, the bell that no longer rang, the silence that filled the inside of the chamber, these were the fingerprints of nothingness itself. Humanity had finally created the void, and here is where the story turns. Because that triumph, that quiet 17th century victory over 2,000 years of philosophical doubt, turned out to be only the beginning. The void Boyle had created looked empty. It sounded empty. It behaved, in every way he could test, as though nothing was inside it. But the deeper instruments came later, centuries later. And when those instruments were finally turned on the very best vacuums humanity could create, they revealed something that no one in Boyle's age could have predicted. The chambers still glowed. Faintly, yes. Almost imperceptibly, but unmistakably. Even after every atom of air had been removed, even after the strongest pumps had drawn out every last molecule, even after the chamber had been sealed and shielded and cooled to temperatures lower than anything found in deep space, something remained inside. A faint shimmer of energy, a whisper of light, a presence too quiet to hear but too persistent to deny. The first cracks in the picture appeared slowly. In the late 19th century, physicists noticed that empty chambers still held a tiny amount of heat. They assumed at first that this was leftover air, residual molecules clinging to the walls. They built better pumps. The heat remained. They cooled the chambers further. The heat remained. They tried again, with more careful seals, with cleaner glass, with techniques their predecessors could never have imagined. The heat remained. By the 20th century, The truth had become impossible to ignore. No matter how perfect the vacuum, no matter how empty the chamber, something always lingered. The void was not empty, after all. Or, if it was empty in the everyday sense, in the sense Boyle would have recognized, it was full in some deeper sense that no one yet understood. Today, in the most advanced laboratories on Earth, scientists can create vacuums so pure that a single cubic centimeter contains fewer particles than the upper atmosphere of the Moon. They can cool those vacuums to temperatures within a fraction of a degree of absolute zero, the lowest temperature physically possible. They can shield them from every known source of radiation. They can wrap them in layers of metal and glass and magnetic fields until nothing from the outside world can possibly reach inside. And still, the chambers glow, not with light you could see, not with heat you could feel, but with a kind of energy that hums beneath the threshold of ordinary perception. An energy that does not come from any atom inside the chamber, because there are no atoms left. An energy that does not come from outside, because nothing outside can reach in. An energy that simply is. An energy that belongs to the space itself. Let that sink in for a moment gently. Take a slow breath. Notice the quiet around you. Notice the sense, the lifelong sense, that the air between you and the wall, between your hand and your face, between your body and the ceiling, is mostly empty. That feeling is not wrong, exactly, but it is incomplete in a way that took humanity thousands of years to begin to understand. The space between things is not nothing. It has never been nothing. From the philosophers of Greece to the pump makers of Magdeburg, from the candle that died in Boyle's chamber to the silent bell that rang without sound, every generation has reached toward the same answer and found it slipping away. Each time we thought we had touched the void revealed another layer. Each time we thought we had emptied a chamber, something stayed behind. And we have never, in the entire history of our species, created a region of space that contains nothing at all. Not once. Not in any laboratory, not in any chamber, not in any imaginable experiment. The void has resisted us. Not because our tools are too weak, but because, as we are about to discover, the void was never going to be empty in the first place. The fabric of reality is woven in such a way that emptiness, in the simple sense we grew up imagining, is not even allowed. This is the first crack, the first quiet realization that the picture you were given as a child, the picture of stars hanging in dark, vacant space, of air as a thin shell around a sleeping planet, of the room around you as mostly nothing with a few solid objects scattered inside it, is a beautiful but partial truth. The real picture is stranger. The real picture is fuller. The real picture is something that took the best minds of the last 4 centuries to even begin to describe. And it gets stranger the closer you look. Because in the chapters ahead, we are going to walk together into territory that would have seemed like magic to the philosophers of Athens, like sorcery to the experimenters of London, like impossibility to the engineers of Magdeburg. We are going to discover that what fills the so-called emptiness is not one thing but many. Invisible oceans, trembling foam, fields that give weight to your bones, a vast pushing pressure that is, even now, stretching the universe apart at a speed that defies belief. Each layer will be stranger than the last. Each crack will widen into something deeper. And by the end of our journey tonight, the air around your body will not feel quite the same as it did when you first lay down to listen. The space between your fingers, the gap between your eyes and the ceiling, the dark room around you with its quiet, familiar shadows, all of it will reveal itself as something more, something fuller, something richer than any philosopher in any garden in any century ever imagined. But we are not there yet. Tonight, we have only just lifted the lid of the first chamber. We have only just seen the faint glow that remains when all the air has been pumped away. We have only just noticed that the bell still rings in silence, that the candle still flickers and dies, that the horses still strain against an invisible pressure that should not, by any old philosophy, exist at all. Rest with that thought for a moment. The void you grew up imagining was already cracking long before you were born. The wisest people who ever lived spent centuries trying to find true nothingness, and not one of them succeeded. Not one of them. And what they found instead, what we are still finding today, is something so unexpected that it changes the meaning of the word emptiness itself. The bell is silent, the candle is dark, the chamber is sealed, and yet inside it, quietly, something hums, something waits, something exists where nothing should be. In the next part of our journey, we will discover the first true layer of that something. We will leave behind the world of pumps and chambers and step into the realm of fields. Invisible oceans of influence that fill every region of space, that carry light and heat and signal, that press against you even now without your knowing. Fields that the philosophers of Greece could never have imagined, but which the magnet on your refrigerator quietly demonstrates every single day. Take a breath. Settle a little deeper. The story we are following tonight is gentle, but it is not small. And the deeper we go, the more the so-called emptiness will reveal itself as the most crowded, most active, most extraordinary thing in the universe. The void was never empty, and the journey to understand what truly fills it has only just begun. Imagine a small kitchen table on a quiet afternoon. There is a paperclip resting on the wood, perfectly still, the kind of object so ordinary that you would never give it a second glance. Now imagine someone slowly bringing a magnet toward it from the other side of the table. The paperclip does not move at first. The magnet drifts closer, still nothing. Then, at some invisible boundary, the paperclip twitches. It slides. It accelerates across the wood, pulled by a force that no eye can see, drawn toward the magnet as if some unseen hand had reached out and tugged on a string. You have watched this 1,000 times, maybe as a child, playing with refrigerator magnets, maybe as an adult, picking up a fallen pin from the floor with a magnetic tool. The motion seems so ordinary that the strangeness of it has been worn smooth by familiarity. But pause with me for a moment and ask the question that almost no one stops to ask. How did the paperclip know the magnet was there? What carried the message across the empty air? What reached out from one piece of metal to another and pulled them together without touching, without sound, without any visible cause at all? For most of human history, this was simply called magic. The Greeks knew about lodestones, those naturally magnetized chunks of iron ore that could lift small metal objects and turn floating needles toward distant points on the horizon. They wrote about them with wonder, and they invented stories to explain them. Some said the stones had souls. Some said they were alive in some quiet, hidden way. None of them could explain what was actually happening, because what was actually happening required an idea that would not exist for another 2,000 years. That idea is the idea of a field, and once you understand it, the world you thought you were living in begins to feel different beneath your skin. Stay with me. We are going to walk slowly through this, because the concept of a field is one of the most beautiful and strangest ideas the human mind has ever produced. It is the idea that began to break apart the old picture of empty space and replace it with something far richer. The space between the magnet and the paperclip is not nothing. The space between your hand and your phone is not nothing. The space between the earth and the sun, vast and dark and seemingly silent, is not nothing. All of it is filled with structure. All of it is woven with influence. All of it is swimming in oceans you cannot see. The story of how we came to know this begins in a small room in London in the early 1800s. A man named Michael Faraday, who had grown up in poverty, who had never been to university, who had taught himself science by reading the books he was hired to bind as a young apprentice, was performing experiments that almost no one else in the scientific world took seriously. He had no formal mathematical training. He could not write equations the way his contemporaries did. What he had instead was a particular kind of imagination, a way of seeing the invisible that bordered on the poetic. Faraday took a sheet of paper. He placed it flat on a table. He put a magnet underneath it. And then, very slowly, very carefully, he sprinkled iron filings onto the paper. The filings did not lie flat the way you might expect. They did not scatter randomly. They organized themselves. They drew themselves into curving lines that arced out from one end of the magnet and looped back around to the other. They formed a pattern so clear and so deliberate that anyone who saw it could not help but feel that something invisible had reached out and shaped the metal dust into a portrait of itself. Picture Faraday leaning over that sheet of paper. Picture him staring at those curving lines and feeling a quiet shock travel up his spine. He was not just looking at a pattern, he was looking at a map. A map of something that filled the space around the magnet, something that existed everywhere at once, something that the iron filings were simply revealing, the way ripples on a pond reveal a stone dropped into still water. The pattern had always been there. The magnet had always been reaching out into the space around it. Faraday had only made that reach visible. He called what he was seeing lines of force. The phrase was almost shy, almost apologetic, as if he himself could hardly believe what he was suggesting. But what he was suggesting was revolutionary. He was saying that the space around a magnet was not empty. It was filled with something, some kind of structure, some kind of invisible web of influence that extended outward in every direction and shaped the behavior of any magnetic object that wandered into its reach. For decades, the rest of the scientific world did not quite know what to make of this. The mathematicians especially were uncomfortable. They had been taught that forces work between objects, point to point, body to body, like invisible strings stretched between two beads. Faraday was suggesting something different. He was suggesting that the force was not in the objects at all. The force was in the space between them. The space itself was alive with structure. The objects only revealed the structure by responding to it. It took another mind, a younger one, to give Faraday's poetic vision its mathematical voice. That mind belonged to a Scottish physicist named James Clerk Maxwell. Maxwell had the kind of intellect that came along once a century. He read Faraday's writings, looked at those simple sketches of iron filings, and saw the equations hiding underneath. He spent years working through the implications, refining and refining, until in the 1860s, he produced a set of equations so elegant and so powerful that they changed the shape of physics forever. Maxwell's equations did something remarkable. They described, in precise mathematical language, the behavior of electric and magnetic fields. They showed that electricity and magnetism were not two separate forces, but two faces of a single phenomenon. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. The two are locked together in a kind of perpetual dance, each one giving rise to the other, each one rippling outward through space at a specific and finite speed. And then Maxwell did something almost mystical with his equations. He calculated the speed at which these ripples would travel. He worked through the numbers, and he arrived at a value that made him stop and look at his own work for a long, careful moment. The speed of those electromagnetic ripples was exactly, almost impossibly exactly, the same speed that astronomers had measured for the speed of light. Light, Maxwell realized, was not a separate thing. Light was a ripple in the electromagnetic field. The sunlight pouring through your window, the glow of the candle on your table, the warmth of the lamp beside your bed, all of it was the same kind of disturbance that Faraday had seen sketched in iron filings. All of it was the electromagnetic field, vibrating, oscillating, carrying energy through space at 300,000 kilometers per second. Let that thought settle for a moment. Every time you have ever opened your eyes and seen anything at all, you have been watching ripples in an invisible ocean that fills every cubic centimeter of the universe. The face of someone you love, the colors of a sunset, the words on a page, the soft glow of a screen, all of it has reached your eyes through the same medium, a medium that was supposed to be empty, a medium that turned out to be one of the most active, most structured, most extraordinary things in existence. But the electromagnetic field carries more than light. Lift your phone for a moment. Notice how it works. Somewhere, perhaps miles away, perhaps in a tower on a distant hill, a transmitter is sending out ripples in the very same field that Faraday first glimpsed in his iron filings. Those ripples travel through walls, through air, through your body, through the wooden frame of your bed, and they arrive at the small antenna in your phone, where they are translated back into voices, into images, into the messages and music and faces of people you may never have met. Radio waves, microwaves, Wi-Fi signals, Bluetooth, every one of them is a ripple in the same ocean. Every one of them is using the same invisible structure to carry information across distances that would have seemed impossible to anyone living a century ago. You are, at this very moment, soaked in this ocean. Right now, lying wherever you are, your body is being passed through by thousands of overlapping signals. Television broadcasts from cities you have never visited. Radio waves from stations that began transmitting before you were born. The faint electromagnetic glow of every star in the sky, traveling across the cosmos for billions of years to gently brush against your skin. You cannot feel them, you cannot hear them, but they are there. They have always been there. And every one of them is a ripple in a field that fills the space your body occupies and the space your body does not occupy with equal weight. Here is where the strangeness deepens. For most of the 19th century, scientists assumed that the electromagnetic field had to be made of something physical. They could not accept the idea of ripples in nothing. Ripples, after all, are always ripples in some substance. Water has ripples. Air has sound waves. Strings have vibrations. So the electromagnetic field, they reasoned, must be a disturbance in some hidden medium that filled all of space. They called this medium the luminiferous ether, the light-bearing ether, a kind of invisible, weightless, frictionless substance that supposedly filled the universe and carried the waves of light the way water carries waves of the sea. This idea was so attractive, so reasonable, so deeply rooted in common sense, that physicists searched for the ether with extraordinary persistence. They built sensitive instruments. They designed elaborate experiments. They were certain that if the Earth was moving through this ether on its journey around the Sun, then they should be able to detect a kind of wind, a measurable drift, as the planet ploughed through the ether like a ship cutting through still water. The most famous of these experiments was conducted in 1887 in Cleveland, Ohio, by two Americans named Albert Michelson and Edward Morley. They built an instrument of remarkable precision. They split a single beam of light in two, sent the two beams along perpendicular paths, and then recombined them. If the Earth was moving through the ether, the two beams should arrive back together slightly out of step, like two swimmers crossing a river in different directions. The difference would be small, but their instrument was sensitive enough to detect it. They ran the experiment. They ran it again. They ran it at different times of year, at different orientations, under every condition they could think of. And every time, the answer was the same. There was no difference. No drift, no wind. The light arrived back perfectly in step, as if the ether did not exist at all. This result baffled physicists for nearly 2 decades. If light was a wave, it needed a medium. But the medium could not be found. The experiments kept returning the same impossible answer. The ether was not there. The answer came, as so many answers in physics do, from a young patent clerk in Switzerland who had no laboratory and no funding and almost no academic position at all. His name was Albert Einstein. And in 1905, he proposed something that no one before him had quite dared to say out loud. Maybe there is no ether. Maybe light does not need a medium. Maybe the electromagnetic field is itself the medium. Maybe space, the so-called emptiness between things, is not a backdrop for fields, but is itself woven from them. This idea was almost too strange to accept. A wave with no water, a ripple with no surface, a vibration in nothing at all. And yet the equations worked. The experiments confirmed it. Light traveled through the vacuum of space because the vacuum of space was not really empty. It was already full of the very field whose vibrations we call light. This is the moment when our old picture of empty space began to collapse in earnest. The void between the stars was not a passive nothingness through which light traveled. The void was already structured. The void was already filled. The light was simply the trembling of that structure, the singing of that fullness, the music held in the air of a room that was never as empty as it seemed. Take a breath here. Slow down for a moment. The story we are telling is gentle, but the implications are vast. Every photon of light that has ever reached your eyes has been a ripple in a field that fills every region of space, including the space inside your own body. The colors of the world are vibrations in something that has no color of its own. The faces you love are pictures painted in the trembling of a medium that no one has ever seen directly. The entire visible world is the surface of an invisible ocean, and you have been swimming in it your whole life without ever noticing that you were wet. And here is the next layer. Because the electromagnetic field is not the only field that fills the universe. It is not even close to the only one. Hold out your hand again. Drop a small object onto the floor. Watch it fall. The motion is so familiar that you would never call it mysterious. But it is. Something has pulled that object downward. Some invisible influence has reached up from the body of the earth and tugged at the falling thing, dragging it toward the center of the planet. We call it gravity. And gravity, like magnetism, is a field. Einstein, the same young man who had banished the ether, spent the next decade after his first great insight building a new picture of gravity. He came to believe that the gravitational field is not so different from the electromagnetic field. It too fills all of space. It too has structure. It too can ripple and bend and stretch. But it does something even stranger than the electromagnetic field. It shapes the geometry of space itself. The earth pulls on you not by reaching out with invisible strings, but by gently warping the fabric of space and time around itself. You fall toward the floor because the floor lies along the natural path that the bent geometry of the field has carved for you. Every step you take, every movement you make, is a journey along the contours of an invisible landscape that you have lived inside since the day you were born. And the fields keep coming. Inside the nucleus of every atom in your body, 2 more fields are at work. Fields so powerful and so short-ranged that for most of human history, we did not even know they existed. The strong nuclear field holds together the protons and neutrons inside atomic nuclei. Without it, the protons would repel each other with electromagnetic force, and every atom in the universe would fly apart in a fraction of a second. The weak nuclear field governs certain forms of radioactive decay, the slow, gentle ticking that powers the heart of stars and the warmth of the planet's core. Both fields are invisible. Both fields fill the space inside every atom that has ever existed. Both fields are woven into the same fabric that carries light and gravity. Picture it now. The space around you is not one ocean, it is many. Layer upon layer, each one occupying the same volume, each one passing through the others without disturbance, each one carrying its own kind of influence. The electromagnetic field shimmering with light, the gravitational field bending gently around every mass, the strong field holding tight around every atomic nucleus in your body, the weak field humming quietly beneath every act of radioactive decay. And there are more besides these. Fields whose names you may never have heard. Fields that physicists describe in equations that take years of study to read fluently. Each one fills the space you are sitting in. Each one fills the space inside your skin. Each one fills the seemingly empty room around your bed. The space between your fingers is woven with fabric. The air in your bedroom is alive with music. The dark beyond your window is an ocean of overlapping currents. The so-called void is not a void at all. It is a tapestry of fields, all of them present at once, all of them whispering to each other, all of them shaping every motion, every photon, every heartbeat in the universe. And yet, even now, we have only described the shallow layer of what fills the void. The fields are real. The fields are everywhere. But beneath the fields, beneath the smooth oceans we have just been describing, there is something stranger still. Something that took physicists much of the 20th century to even begin to glimpse. Something that does not behave like a smooth pattern of lines of force. Something that does not lie quietly waiting for a magnet or a falling object to disturb it. Beneath the fields, the void itself trembles, not metaphorically, literally. At scales smaller than any microscope can ever see, the fabric of space is restless. It hums with a kind of activity that defies the calm picture we have just built. Particles flicker in and out of existence in a fraction of a second. Energy appears from nothing and vanishes back into nothing before the universe has time to notice. The smooth ocean of fields, the gentle ripples that carry light and gravity and nuclear force, sits on top of a deeper layer that boils with a quiet, ceaseless storm. Tonight, we have learned to feel the first ocean. We have learned that the space around us is not empty, but woven, structured, alive with invisible influence. We have walked from the iron filings of Faraday to the equations of Maxwell to the bent geometry of Einstein. We have stood at the edge of a picture in which every cubic centimeter of so-called nothing is in fact threaded with overlapping fields. We have come a long way from the candle dying silently in Boyle's chamber. But this is only the surface. Beneath the ocean of fields, there is another layer, a layer so strange that for decades the physicists who first encountered it could hardly believe their own mathematics. A layer in which emptiness is not still, not silent, not patient. A layer in which the void itself is alive in a way that would have been unthinkable to the philosophers of any earlier age. Rest gently for now. Take a slow breath and feel the air around you. Feel the fields you cannot see. Feel the magnet of the earth quietly pulling on every cell of your body. Feel the light of distant stars passing through your eyelids on its long journey across the electromagnetic ocean. Feel the soft hum of gravity bending the path of every breath you take. These are the things that fill the visible layer of the void. These are the oceans you have been swimming in since the moment you were born. And in the next part of our journey, we will dive deeper still. We will leave the smooth surface of the fields and descend into the trembling foam beneath them. We will discover that the deepest layer of so-called empty space is not calm at all. It is restless. It is alive. It is the strangest thing that physics has ever found. The bell still hangs in the chamber. The fields still ripple all around you. And somewhere just beneath them, quietly, the void itself is beginning to tremble. Imagine, for a moment, a small pond in the countryside, on a windless summer night. The air is warm, the crickets are quiet, the sky above is full of stars that hardly move. You walk slowly along the path that leads to the edge of the water, and you stop at the bank. From where you are standing, the surface of the pond looks like a single sheet of dark glass, perfectly smooth, perfectly still. So still that the reflection of the stars above seems painted onto the water rather than floating on it. Stay with that image for a few breaths. The stillness of the pond is not something most of us see often in our daily lives. There is something almost holy about it. A quiet so complete that the surface seems to hold its breath, refusing to move, refusing to ripple, refusing even to acknowledge the soft pressure of the warm summer air. Now, in your imagination, take one step closer. Lean down a little. Bring your eyes nearer to the water. From this new distance, the surface no longer looks like glass. There are faint movements you could not see before, a slight tremor near the reeds, a small drifting patch where an insect must have landed and lifted away again. Tiny circular ripples expanding and dying so softly that they vanish before they reach the bank. The pond is not as still as it seemed. It is moving in 100 small ways that were simply too quiet for you to notice from a distance. Lean closer still. Bring your face down until it is just above the surface. Now the water is alive. There are vibrations passing through it constantly. Pressure waves from the wind that is not quite still. Microscopic disturbances from microorganisms moving through their tiny worlds. Trembling so faint that you can only see it, because you have brought yourself this close, this patient, this attentive. The pond has not changed. The pond was always this way. You have simply moved nearer to the truth of it. Hold that image gently. It is going to guide us through one of the strangest discoveries in the history of science. Because what is true of the pond is true of the void itself. From a great distance, from the comfortable scale of our daily lives, the space around us looks perfectly empty. Lean closer, and we begin to see the fields we discovered in the last chapter, the invisible oceans of influence that fill every cubic centimeter of the universe. But lean closer still. Bring your imagination down to a scale so small that no microscope on Earth could ever follow it. And what you will find there is something that broke the minds of the physicists who first glimpsed it. The void trembles, not gently, not occasionally, constantly, furiously. At the smaller scales of existence, the so-called nothingness between things is not still at all. It is a storm, a boil, a churning, ceaseless activity that has been going on since the universe began and will continue going on long after every star has burned itself out. Let us walk into this slowly, because this is the part where the picture of reality you have carried since childhood begins to feel like a thin curtain that someone is gently pulling aside. The story begins in the 1920s, in a generation of young physicists who were just beginning to peer into the world of the atom. They had inherited a comfortable picture from their predecessors. Atoms were tiny solar systems. Electrons orbited around nuclei like planets around suns. Energy moved in smooth, predictable waves. The universe was strange at small scales, but it was still a universe that could be drawn on a chalkboard with a steady hand. What they discovered, over the course of just a few astonishing years, was that this picture was wrong. Not slightly wrong, deeply, structurally wrong, in a way that no amount of patching could repair. The world at the smallest scales did not behave like a smaller version of the world at large scales. It behaved according to rules that seemed almost designed to violate every intuition the human mind had developed over millions of years of evolution. The new physics they built to describe this hidden world was called quantum mechanics. It was so strange, so counterintuitive, that even its creators sometimes confessed that they did not really understand it. One of them, the physicist Niels Bohr, once said that anyone who is not shocked by quantum theory has not understood it. Another, Richard Feynman, said decades later that nobody really understands it. They did not mean that the theory was wrong. They meant that the theory was so deeply strange that the human mind could only follow it the way a child follows a story in a foreign language. The grammar was there. The meaning kept slipping away. But within the equations of this new physics, something extraordinary was hidden. It took a while for anyone to notice it, and when they did, it changed forever what the word emptiness could mean. The clue was hidden inside a principle discovered by a young German physicist named Werner Heisenberg. He showed, in 1927, that there are certain pairs of quantities in nature that can never be known precisely at the same time. The position of a particle and the speed of that particle, for example, can never both be measured to perfect accuracy. The more precisely you pin down one, the more uncertain the other becomes. This was not a limit of our instruments. This was a fundamental feature of reality. The universe simply does not allow both numbers to exist with perfect sharpness at the same moment. This idea, which became known as the uncertainty principle, was startling enough on its own. But there was a hidden consequence buried inside it, and that consequence is what we are interested in tonight. The same principle that applies to position and speed also applies to energy and time. The shorter the period of time you consider, the more uncertain the energy of any region of space becomes. And here is where things start to feel like a quiet form of vertigo. If you make the period of time short enough, the uncertainty in energy becomes so large that energy can effectively appear from nothing, exist for an unimaginably brief moment, and vanish again, all without violating any law of physics. Read that sentence again, slowly, because it is the seed of everything that follows. The laws of quantum mechanics do not forbid energy from appearing out of so-called empty space, as long as it appears briefly enough and vanishes again before the universe has time to notice. The shorter the visit, the more energy is allowed. The longer the visit, the less energy is allowed. But the visits themselves cannot be prevented. They are not a special event. They are not a rare accident. They are happening constantly, everywhere, in every cubic centimeter of every region of space in the entire universe. The physicists who first realized this could hardly believe what their own equations were telling them. They sat with the mathematics and ran the calculations again and again, looking for the mistake. But there was no mistake. The equations were clear, and the picture they painted was so strange that it required a new vocabulary just to describe it. They began to speak of virtual particles. The word virtual here does not mean fake. It means something more subtle. It means a kind of existence that is so brief, so flickering, so far below the threshold of ordinary observation, that the particle never quite settles into the kind of solid reality that you and I would call existing. These virtual particles appear in pairs, one particle and its antiparticle, born together out of the trembling of the field. They fly apart for a fraction of a second, and then they meet again and annihilate each other, returning the energy they borrowed, leaving no trace, leaving no record, except for the faint statistical fingerprint they leave on the behavior of everything around them. Picture it. In every cubic centimeter of the space around your body, right now, this is happening. Pairs of particles are flickering into existence and vanishing again at a rate so fast that no clock could measure it. Electrons and their antimatter twins, quarks and their antimatter twins, photons borrowed from the void and returned a moment later. Every kind of particle the universe is capable of producing is being produced and unproduced constantly, in numbers so vast that the human mind cannot hold the figure. This is the trembling of the pond when your face is close enough to see it. This is the foam beneath the smooth surface of the fields. This is what physicists came to call the quantum vacuum. And the word vacuum here is almost a kind of joke, because the quantum vacuum is the least empty thing that has ever been described. For a long time, this all sounded like an interesting mathematical fiction. The equations predicted these flickering particles, but they were so brief, so fleeting, so impossible to catch in the act that some physicists wondered whether they should be taken seriously as a real phenomenon. Maybe the math was just a useful trick. Maybe the virtual particles were a kind of accounting device, a way of keeping track of the energy of the field without claiming that anything was actually appearing and disappearing in the void. The doubt did not last forever, because the quantum vacuum, it turned out, was not just an idea, it was something you could measure. It was something you could touch, in the indirect way that physicists touch the invisible. And the experiment that proved it is one of the most beautiful and most quietly astonishing experiments in the history of science. The story takes us to the Netherlands in 1948. A Dutch physicist named Hendrik Casimir was working on a problem that had nothing obviously to do with the vacuum. He was studying the behavior of certain liquids and the forces between large molecules. But in the middle of his calculations, he noticed something strange. The mathematics seemed to suggest that if you took two perfectly flat, perfectly parallel metal plates and brought them extremely close together in a vacuum, they should feel a tiny but measurable force pushing them toward each other. A force that did not come from gravity. A force that did not come from electromagnetism in any ordinary sense. A force that seemed to come from the empty space between the plates itself. Casimir worked through the calculation again. The result was the same. He proposed it in a short, modest paper, and for decades, nobody could quite measure the force directly. The plates had to be too smooth, too flat, too close together for the technology of the time, so the predictions sat there in the literature, waiting, while the physicists who knew about it debated whether it would ever really be confirmed. It was confirmed. In the 1990s, using extraordinarily precise instruments, experimentalists finally managed to bring two metal surfaces close enough together to detect the force Casimir had predicted half a century earlier. The plates pulled toward each other. The force was tiny, but it was there. It was exactly what the equations had said it should be. Now here is what makes this experiment so important, so quietly devastating to the old picture of empty space. Stop for a moment and think about what the experiment was actually showing. There were two metal plates. The space between them had been emptied of air, emptied of any conceivable normal source of pressure, and yet a force was pushing the plates together, a force that had to be coming from something. A force that was real enough to bend the most sensitive measuring instruments humanity had ever built. The explanation Casimir had offered, and the explanation that the experiments confirmed, was this: the space between the plates is not empty. It is filled with the quantum vacuum, with all those flickering virtual particles, with all those constant trembling fluctuations of energy that are happening everywhere all the time. Outside the plates, the same trembling is happening, but the plates themselves act like a filter. They restrict which kinds of fluctuations can fit in the narrow space between them. Some wavelengths of virtual particle activity are too long to squeeze in. Others fit easily. The result is that the trembling inside the gap is slightly less intense than the trembling outside it. And that imbalance, that tiny difference in the pressure of nothing, pushes the plates together. Two metal plates placed extremely close in a vacuum are gently pushed together by the trembling of nothing. Stay with that sentence for a moment. Let it sit. The most carefully prepared emptiness humanity can create is not empty. It pushes. It exerts pressure. It moves real, solid metal in a real, solid laboratory. The void has weight, the void has muscle, the void has something it wants to do, and given the right conditions, it does it. This is not a quirk of the experiment. This is not a special property of metal plates, or of laboratories, or of cold-sealed chambers. The quantum vacuum is everywhere. The trembling that pushed those plates together is happening in every region of space in the universe, at every moment, at every point. The reason we do not normally feel it is that the trembling is symmetrical. It pushes on us equally from every direction, so the net force is zero. But when you set up the right geometry, when you place a barrier in the field and break the symmetry, the trembling reveals itself. It comes forward. It announces, in the quiet voice of a measured force, that it has been here the whole time. Now, let us widen the lens. This is the moment to step back from the laboratory and remember where we are. You are lying somewhere, in a bed perhaps, or on a couch, in a quiet room with the light low. The world around you feels solid. The pillow under your head feels still. The cup of tea on the table beside you, if there is one, sits patiently, cooling slowly, doing nothing visibly dramatic. The air in the room is calm, and yet, in every cubic centimeter of that room, the quantum vacuum is trembling. Inside the pillow, inside the cup, inside the air, inside your own body. The same flickering activity that pushed Casimir's metal plates together is happening at scales finer than any instrument can directly see. Pairs of particles are being born and dying. Energy is appearing and vanishing. The fields we met in the last chapter, all those invisible oceans that fill space, are not lying flat and quiet. They are trembling at every point. They are restless at every scale. They are a foam of activity, and you are made of the same foam. Take a slow breath. Notice the air entering your lungs. Notice the gentle expansion of your chest. The air that just filled your body is not still. The atoms inside it are not still. The space between those atoms is not still. At scales unimaginably small, every bit of that air is humming with the same trembling that fills the gap between Casimir's plates. Your breath is full of foam. Your blood is full of foam. The cells of your heart, contracting in their quiet rhythm, are made of atoms whose interiors hum with virtual particles flickering into and out of existence faster than any clock can mark. You are not separate from this trembling. You are not floating above it. You are made of the same restless fabric that fills the empty space between the stars. The matter of your body and the so-called nothing of the void are not two different substances. They are the same substance, organized at different scales, vibrating at different frequencies, but built out of the same fundamental restlessness that runs all the way down to the smallest layer of reality. This is a strange thing to sit with, gently. Most of us have spent our lives feeling solid, feeling separate, feeling like little islands of substance floating in a sea of mostly nothing. The truth that physics has slowly uncovered is almost the inverse of that feeling. The substance is mostly nothing. The nothing is mostly substance. The boundary between body and void is not a wall but a soft transition, a place where one kind of organization gives way to another, where the foam takes on a particular pattern that we have learned to call by your name. This idea is so strange that for a long time, even after the experiments confirmed it, physicists struggled to accept what the equations were saying. There was something almost embarrassing about the picture. Calculations of the energy density of the quantum vacuum gave answers that were absurdly large. If every cubic centimeter of space really did contain all this flickering activity, then the total energy of the vacuum should be enormous. Enormous enough to bend the geometry of the entire universe in dramatic ways. Enormous enough to be the dominant feature of cosmology. And yet, when astronomers looked out at the universe, they did not see the effects that such an enormous vacuum energy should produce. The universe was much calmer than the theory predicted. This mismatch between theoretical prediction and observed reality is now called the vacuum catastrophe. It is sometimes also called the worst prediction in the history of physics. Not because the prediction is wrong in some small way, but because the predicted value and the observed value differ by a factor so vast that it has more zeros than any number you have ever read in your life. Physicists do not know how to resolve this discrepancy. There are guesses, there are partial models, there are hints, but no one yet has a complete answer to the question of why the trembling vacuum, which is so clearly real, behaves the way it does at cosmic scales. We will return to this puzzle in a later chapter because it is connected to one of the deepest mysteries in modern cosmology. For tonight, simply hold the picture. The vacuum is not empty. The vacuum is not still. The vacuum is full of an activity so intense, so ceaseless, so unimaginable in scale, that even the physicists who have spent their lives studying it confess that they do not entirely understand what they are looking at. And this activity is not happening somewhere far away. It is not confined to particle accelerators or to deep space. It is happening here, now, in the space between your eyelashes, in the air above your skin, in the gentle curve where your fingers meet the blanket, in the slow rising warmth of the tea beside your bed. The trembling foam beneath reality is everywhere. It is the floor of the universe. It is the surface on which every visible thing is built. Let us return to our pond for a moment. The image we started with all those minutes ago, the dark, still surface that turned out to be moving in 100 small ways once you brought your face close enough to see them. Imagine bringing your face closer still, closer than any human eye can ever truly go, closer than the smallest microscope can reach. Imagine descending through the surface, through the molecules of water, through the atoms inside those molecules, through the nuclei inside those atoms, until you arrive at a scale so small that the very concept of distance begins to lose its ordinary meaning. At that scale, the pond does not exist. The water does not exist. There is no smooth surface, no liquid, no familiar shape of any kind. There is only the trembling. Pure, ceaseless, structureless trembling, foam, activity without object. The quantum vacuum revealing itself as the deepest layer that physics has ever been able to point at, the layer beneath which we do not yet know how to look. And that same foam is inside you, right now, tonight. The trembling that fills the bottom of the pond is the same trembling that fills your bones, your blood, your breath, your thoughts. You and the foam are not two things. You are a particular pattern that the foam has organized itself into, a pattern complex enough to wonder about the foam, a pattern delicate enough to drift towards sleep while listening to a quiet voice describe the strangeness of its own origin. Rest gently with this for a moment. The chamber has been sealed. The candle has gone dark. The bell has fallen silent. The fields have shimmered into view, oceans of invisible influence filling every direction. And now, beneath those fields, the void itself has begun to tremble. It has revealed that it was never still, never empty, never quiet, always foaming, always restless, always alive in a way that no philosophy and no intuition could have predicted. But we are not finished yet. There is one more layer to uncover before we step back and let you sleep tonight. Because if the trembling vacuum is the floor, then there is one particular field within it that does something even stranger than the others. A field that does not just carry light or pull on falling objects. A field that gives every particle of matter, including every cell in your body, the property we call weight. A field that, without exaggeration, makes you possible. In the next part of our journey, we will meet that field. We will hear the story of the decades-long search to confirm it, the largest machine ever built by human hands, and the quiet morning when the announcement finally came that the search had succeeded. The trembling foam is the floor. But the floor itself has a structure, and within that structure, one particular invisible substance gives all matter the heaviness it carries through the world. For now, breathe slowly. Notice the air. Notice the foam. Notice the trembling that has always been inside you, beneath every layer of skin and bone and thought, the quiet, ceaseless hum of the deepest emptiness that has ever been described. The void was never empty. The pond was never still, and what fills the gap between your fingers, the gap between your eyes and the ceiling, The gap between the Earth and the farthest star is not nothing at all. It is foam. It is trembling. It is the most active stillness in the universe. Let us slow down for a moment. The journey so far has carried you through some of the strangest territory in modern physics. We started with a simple assumption that space is empty. We watched that assumption crack in the laboratories of 17th century gentlemen. We discovered the invisible oceans of fields that fill every cubic centimeter of the universe. And then we descended into the trembling foam beneath those fields, the quantum vacuum, where particles flicker into and out of existence faster than any clock can measure. Take a breath. Let the trembling fade for a little while, because the next part of our story is gentler, or at least it begins gently. It is the part of the story that gives the rest of it a place to stand, a floor, a something to hold on to. And the analogy we are going to use to walk through it is one of the most useful, most strangely beautiful images that physics has ever produced. Imagine, for a moment, that you are wading into a swimming pool. The water is warm, the light is soft. You step in slowly, the way you might on a quiet evening when the pool is empty and the day is winding down. At first, the water reaches only to your ankles. You can walk freely. The water barely touches you. You step in deeper. Now the water reaches your knees, and walking has become slightly harder. There is a gentle resistance against your legs. You take another step. Now the water is at your waist. Each movement requires a little more effort than before. The water pushes back. It clings to you. It slows you down. Now, imagine that instead of an ordinary swimming pool, you have stepped into a pool filled not with water, but with something thicker. A pool filled with honey, or syrup. Imagine that same slow walk through a pool of warm syrup. Now every step is a struggle. The substance drags against every part of your body. You can move, but moving costs you. The thicker the substance, the harder the motion becomes. The thicker the substance, the heavier you feel. Hold that image gently. We are going to spend the rest of this chapter living inside it. Because what physicists discovered in the second half of the 20th century is that the universe itself is filled with something not unlike that pool of syrup. Not made of water, not made of honey, not made of any ordinary substance you could touch or taste, but a field, an invisible field. A field that fills every region of space in the entire universe, including the space inside your body and the space between every star. This field is called the Higgs field, and without it, you would not exist. The chair you are sitting on would not exist. The earth beneath you would not exist. The sun would never have ignited. The atoms inside every cell of your body would not be able to hold themselves together. The very property we call weight, the heaviness of objects, the resistance of things to being pushed around, the mass that gives substance to substance, would not be a feature of the universe at all. Stay with me, because this idea is so quietly extraordinary that it changed the shape of physics forever when it was first proposed, and it took nearly 50 years and the largest machine ever built by human hands to confirm. To understand why the Higgs field matters, we need to think for a moment about what mass actually is. You probably grew up thinking of mass as simply how much stuff something is made of. A bowling ball has more mass than a feather because the bowling ball has more stuff inside it. This way of thinking is comfortable and intuitive, and for everyday life it works perfectly well. But when physicists began studying particles in the 20th century, they ran into a strange and embarrassing problem. They could write down all the equations describing how particles move and interact. The equations were beautiful. They were elegant. They explained almost everything they were supposed to explain. There was just one difficulty. The equations would not allow particles to have mass. Not in a small way, not in a partial way, in a complete, and devastating way. If physicists wrote down the natural equations for the fundamental particles, the math demanded that every particle in the universe move at the speed of light, weighing nothing, possessing no inertia, no heaviness, no substance at all. The universe, according to the equations, should be a perpetual storm of massless particles flying past each other forever, never combining, never settling, never forming anything stable enough to be called a thing. And yet the universe is clearly not like that. You have hands, you have bones, the earth has a surface, the stars have shape, mass exists. Heaviness is a feature of the world we live in. So either the equations were wrong, or something was missing from them, something that the original mathematics had not yet included. In the 1960s, several physicists working independently in different countries began to suspect what that something might be. One of them was a quiet, gentle Englishman named Peter Higgs, working in Edinburgh. He was not particularly famous at the time. He was not the kind of physicist who held press conferences or appeared in popular magazines. He was a careful, methodical thinker who liked to walk in the Scottish hills and chew slowly on difficult problems. In 1964, Higgs published a short paper, less than 2 pages long, in which he proposed something remarkable. He suggested that the universe is filled with a kind of invisible field, similar in some ways to the electromagnetic field, but with a crucial difference. Most fields, including the electromagnetic one, average out to zero when they are undisturbed. They are like a calm sea with no waves, sitting at a default value of nothing in particular. But this new field Higgs proposed was different. Even in its lowest, most settled, most undisturbed state, this field still had a value. It still had a presence. It was never zero. It was always there, like a thin syrup soaked into every corner of the cosmos. And here was the heart of his idea. As particles moved through this everywhere syrup, they would interact with it. Some particles, by their nature, would interact very weakly. The field would barely notice them. Those particles would pass through almost unaffected, and we would experience them as having very little mass. Other particles would interact more strongly. The field would cling to them. It would slow them down. It would drag against them as they tried to move. And those particles, the ones the field clung to most stubbornly, we would experience as being very massive. In this picture, mass is not something a particle has all by itself. Mass is a relationship. Mass is the conversation between a particle and the Higgs field. The stronger the conversation, the heavier the particle. The weaker the conversation, the lighter it is. And without the field, without that all-pervading syrup soaked through every region of the universe, no particle would have mass at all. The conversation would not exist. The drag would not exist. Everything would zip away at the speed of light, weightless and untouchable. Picture it gently. Imagine the entire universe filled, edge to edge, with this invisible substance, not pooling in certain places, not thicker in some regions than others, filling everything. The space between the stars, the space inside your kitchen, the space between every electron and proton in every atom of your body. Every cubic centimeter of the cosmos contains this field, and every particle of matter is constantly wading through it, constantly feeling its drag, constantly being given the property we call weight by the simple fact that the syrup is there. When Peter Higgs first proposed this, the response was, frankly, polite skepticism. The idea was elegant, the mathematics worked, it solved the embarrassing problem of where mass came from. But it required physicists to accept that the universe was filled with a hidden field that no one had ever directly observed. A field that was, in principle, detectable, but only if you could find a way to disturb it strongly enough to make it ring. To understand what disturbing the field would mean, it helps to remember something we learned in earlier chapters. Fields, when disturbed, produce ripples. The electromagnetic field, when disturbed, produces ripples we call photons, the particles of light. The gravitational field, when disturbed strongly enough, produces gravitational waves. Every field has its own kind of ripple, its own kind of particle, that appears when the field is shaken hard enough. If the Higgs field really existed, then by the same logic, it ought to have a ripple of its own, a particle, a signature, a messenger that would only appear if you could shake the field with enough energy to make it visible. This particle came to be called the Higgs boson, and finding it became one of the great quests of modern physics. Not because the particle itself was the point. The particle was almost a side effect. The real prize was the field. The Higgs boson was important because finding it would confirm that the field was real. The boson was the fingerprint. The field was the hand. For decades, physicists chased this fingerprint. They built bigger and bigger machines. Particle accelerators, vast underground rings of magnets and pipes, in which protons were sped up to nearly the speed of light and smashed together with such violence that the energy released could, in theory, ring the Higgs field hard enough to produce its signature ripple. The trouble was, no one knew exactly how heavy the Higgs boson would be. The equations gave a range, but not a single number. So the search had to be conducted across a wide territory of possible energies, year after year, accelerator after accelerator, with the results always coming back the same. Not yet, not yet, not here, not at this energy, try higher. In the early 2000s, physicists from dozens of countries gathered together to build the largest scientific instrument ever constructed. Beneath the border between France and Switzerland, in a circular tunnel 27 kilometers around, they assembled a machine called the Large Hadron Collider. It cost billions. It involved tens of thousands of engineers and scientists. It required cooling its magnets to temperatures colder than deep space. It was, by almost any measure, the most ambitious experiment humanity had ever attempted. The purpose of this machine, the deepest purpose at the heart of all that effort and money and patience, was simple. Find the Higgs boson, confirm the field, show that the picture of mass that physicists had been working with for half a century was real. The machine turned on in 2008. There were setbacks, equipment failures, years of delicate calibration. Slowly, painstakingly, the collider began to produce collisions, billions and billions of them, each one a tiny moment in which two protons met head-on at nearly the speed of light and disintegrated into showers of new particles. Most of those collisions produced nothing surprising. The particles that came flying out of them were the familiar ones, the ones already in the textbooks. But every so often, very rarely, a collision might produce something different. A flicker, a signature, a pattern that matched what the theorists had predicted the Higgs boson would look like. For 3 years, the data accumulated. Thousands of physicists worked through it. They were looking for a tiny statistical bulge, a slight excess of certain kinds of decay patterns. That would mean a Higgs boson had been briefly produced and had then dissolved into other particles a fraction of a second later. And then, on the morning of July 4th, 2012, the announcement came. Imagine the room. Imagine a packed auditorium at the European laboratory called CERN, the place where the collider was housed. Imagine physicists from around the world, some of them present in person, others watching by video link in laboratories on every continent. Imagine the slow, careful presentations as two separate experimental teams stepped to the podium, one after the other, and showed their data. Imagine the bulge in the graph. Imagine the gentle, restrained excitement in the voices of the speakers, the kind of excitement that scientists allow themselves only when they are very, very sure. The two teams had found it, independently, using different detectors, looking at different collisions. They had both found the same signal at the same energy, a new particle, a particle that behaved exactly as the Higgs boson was predicted to behave. In the audience, an old man with white hair and a kind face was wiping tears from his eyes. He was 83 years old. 48 years had passed since he had written the short paper proposing the field that now bore his name. Peter Higgs had lived long enough to see the confirmation of an idea he had quietly carried with him for nearly half a century. The next year, he would receive the Nobel Prize for the same work. But on that morning in 2012, what he received was something even more profound. He received the knowledge that the universe really did contain the invisible substance he had imagined. The field was real, the syrup was real, the everywhere drag that gives every particle its mass was real, and humanity had finally heard it ring. Sit with this moment for a little while. Take a slow breath. Notice the weight of your body pressing into whatever surface you are resting on. That weight, the simple heaviness of your own form, is not a property your atoms carry on their own. It is a gift from the Higgs field. Every electron in every atom of your skin, every quark in every proton in every nucleus, owes some part of its mass to the constant invisible drag of the field that fills the universe. Without that field, the electrons in your body would not orbit the nuclei. The atoms would not form. The molecules of your cells would unravel. The very structure of you would dissolve into massless light, scattering at the speed of all things, never lingering long enough to be called a body. The Higgs field is the reason you are something rather than nothing. The Higgs field is the reason your body has substance. The Higgs field is the reason stars can collapse inward under their own weight and ignite into the long, slow furnaces that warm the planets. The Higgs field is the reason the Earth coalesced into a sphere of rock and water, rather than dispersing into a thin cloud of unbound radiation drifting forever across the cosmos. Picture, for a moment, a single grain of sand, a small one, the kind you might find on a beach, brushing it from your skin without thinking. It weighs almost nothing. It sits in the palm of your hand and barely registers. You could blow it away with a soft breath. It is one of the most insignificant objects you could possibly hold. Now picture the field that gave that single grain of sand its weight. The Higgs field stretches across every cubic meter of every region of space in the observable universe. It fills the dark vastness between galaxies. It fills the cores of stars. It fills the tunnels of every cave on every planet. It fills the inside of every atom in every body of every living thing in every world that has ever existed. It is unimaginably vast. It is everywhere. And every particle in that tiny grain of sand, every electron, every quark, every fragment of mass that adds up to give the grain its faint, gentle heaviness, is participating in a relationship with this cosmic field that fills the entire universe. A grain of sand, a field the size of everything. The two are inseparable. The smaller object would not exist without the larger one. The smaller object is, in a sense, a tiny knot tied in the fabric of the larger one, a place where the field has clung especially tightly, given a particular pattern of particles, a particular kind of substance, woven a small piece of cosmos into the shape we recognize as matter. Look at your own hand, lying still wherever you are resting. Imagine the grain of sand in your palm. Now imagine that your entire hand is made of nothing but countless tiny knots in the same field. Every fingertip, every line on every palm, every bone, every vein, every cell, every atom, all of it is the universe-filled syrup wrapping itself around particles and giving those particles the property of weight. You are a sculpture made of trembling foam, woven through with invisible syrup, given shape by a field whose existence was only confirmed in your own lifetime. This is the steady floor we needed before going any deeper. The trembling vacuum of the last chapter is still there, still humming beneath everything. But on top of that trembling, The Higgs field lies like a calm second layer, a thicker presence, a slower kind of fullness that gives the visible universe its substance and its solidity. Without the foam, nothing could exist at all. Without the syrup, the foam could not organize itself into anything that lasts long enough to be called a thing. Take another breath. Feel the gentle resistance of the air in your lungs. Feel the pressure of your body against the surface beneath you. That pressure is the weight of every atom of your body interacting with the gravitational field of the Earth. But before any of those atoms could have weight in the first place, they had to interact with the Higgs field. The chain of fields is long, and each link of it is invisible, and each link of it is essential. This is also, gently, the moment to begin preparing for the next layer of our story, because the Higgs field, as remarkable as it is only one of several fields that fill the vacuum. We have met the electromagnetic field, the gravitational field, the strong and weak nuclear fields, the trembling quantum foam, and now the Higgs field. Each of them fills space. Each of them shapes some piece of what we call reality. Each of them lives quietly in what looks to our eyes like emptiness. But there is something else. Something that physicists only began to discover near the end of the last century. Something that does not behave like any of the fields we have met so far. Something that does not draw nearby objects together, the way gravity does. Something that does not carry light or hold atoms together. Something that does the opposite. Something that pushes. Something that, even now, in this quiet moment as you rest and breathe and listen, is pushing the universe apart at a speed that is itself slowly increasing. We do not entirely understand it. We do not have a confident name for it. We call it dark energy, but the word dark here means hidden, not evil, not threatening. It means we do not yet know what it is. We only know that it is real, that it is everywhere, that it is by far the most abundant ingredient in the universe, and that it is doing something to the cosmos at the largest scales that no physicist before the 1990s had predicted. This is the most unsettling part of the story, and we will walk through it slowly, the way we have walked through every part. There is nothing to fear in it. The universe expanding does not threaten you tonight. Galaxies drifting apart does not change the warmth of the room you are resting in, but the picture it paints, the picture of the void as not only full but actively pushing, actively swelling, actively dominating the structure of everything, is one of the strangest discoveries in the entire history of human thought. For now, rest gently. Let the trembling foam settle. Let the syrup of the Higgs field hold you up. Feel the weight of your own body, and know that the weight is on loan. It is not a possession. It is a gift from a field that stretches across the entire universe. Every cell of you is wading through that field, every moment of your life, slowly and patiently, the way a swimmer wades through warm water on a quiet summer evening. The void is not empty. The void is full of fields. The fields are full of foam. The foam is full of activity. And on top of all of it, the Higgs field is full of the heaviness that gives you a body, a shape, a place in the world. The universe is the most crowded thing that has ever been imagined. And in the next chapter, we will discover that even the crowd inside the void is being pushed gently, ceaselessly, mysteriously, outward, by something we have only just begun to see, by something that may be the most abundant ingredient in everything that exists. Rest now. The story is gentle still. The strangeness ahead is also gentle, in its own slow way, and the syrup of the field will hold you while you listen. Let us begin this chapter the way astronomers themselves often begin, by looking up. Picture yourself standing in an open field on a cold, clear night, somewhere far from the lights of any city. The sky above you is full of stars, thousands of them, bright ones, faint ones, scattered ones, clustered ones. And beyond the stars you can see with your eyes, in the quiet way that modern people know things, that there are billions more. You know that the small fuzzy patches between the stars are not clouds, but galaxies, each one containing billions of suns of its own. You know that the universe is unimaginably large. You know that the light reaching your eyes from some of those distant galaxies has been traveling for billions of years to arrive at this single quiet moment of your looking. Now hold that picture gently in your mind, because the story we are going to walk through in this chapter is one of the most disorienting discoveries in the entire history of human thought. And it begins with a group of astronomers who were trying to measure something they thought they already understood. In the 1990s, astronomers around the world were working on a quiet and confident project. They wanted to measure exactly how fast the expansion of the universe was slowing down. The expansion itself was not in doubt. It had been known since the 1920s that the universe was getting bigger. Distant galaxies were drifting apart from one another. The light from those galaxies was stretched out by their motion, shifted toward redder wavelengths, in a pattern that pointed clearly to a cosmos that had been expanding for billions of years. This expansion had a comfortable story attached to it. The universe had begun, long ago, in a hot, dense state. It had been flying outward ever since. And gravity, the gentle but relentless attraction of all matter to all other matter, should have been slowing that outward flight down. Galaxies pulled on galaxies. Stars pulled on stars. Every piece of matter in the universe pulled on every other piece. So the expansion, while still happening, ought to be gradually losing its strength. The universe was a thrown ball, rising through the air, slowing as gravity tugged at it from below. The question astronomers were asking in the 1990s was not whether this was true. They were sure it was true. The question was simply how fast the slowing was happening. By measuring that rate of deceleration, they hoped to figure out what the long-term fate of the universe would be. Would gravity eventually win, pulling everything back together into a final hot collapse? Or would the universe just barely keep expanding forever, slowing but never quite stopping? Or was it somewhere in between, settling into a long, gentle drift? To find out, two competing teams of astronomers around the world began an enormous project. They studied a particular kind of stellar explosion called a Type 1, a supernova. These are dying stars that explode in a very consistent way. They are so consistent, in fact, that astronomers can use them as cosmic mile markers. By knowing how bright a Type 1 a supernova really is, and by comparing that to how bright it looks in our sky, you can calculate exactly how far away the exploded star was. Find one of these supernovae in a distant galaxy, measure its brightness, and you have a precise measurement of how far light has traveled to reach you. Measure the redshift of that same supernova, and you know how much the universe has expanded during that light's long journey to your telescope. Do this for enough supernovae, at enough different distances, and you can map out the history of the expansion itself. You can see how fast the universe was expanding in the distant past, in the medium past, and in the recent past. You can watch the rate of expansion change over cosmic time. And by comparing those rates, you can answer the question, how quickly is the universe slowing down? Two teams, working independently, spent years on this project. They scanned the sky. They found supernova after supernova in distant galaxies. They measured the brightnesses. They calculated the distances. They lined up the data. And in 1998, both teams arrived at the same answer. The answer was wrong. Not slightly wrong. Not surprising in some small detail. Completely, dramatically, impossibly wrong. The numbers did not show a universe that was slowing down. The numbers showed something that no one had predicted, that no one had even seriously considered as a possibility. The universe was not decelerating, it was accelerating. The expansion was getting faster. Imagine the moment when those astronomers first stared at their results and realized what they were seeing. Imagine the disbelief. Galaxies should be slowing as they drift apart from each other, dragged on by mutual gravity. Instead, they were speeding up. The distant past had a slower expansion. The recent past had a faster one. The motion of the cosmos was not winding down like a thrown ball. The motion of the cosmos was being pushed. Pushed by what? Nothing in the equations of physics, as they stood at the time, predicted such a thing. Nothing in any known theory required it. Nothing in the long history of astronomical observation hinted at it. And yet there it was, written in light from exploding stars in galaxies billions of years away. The universe was being pushed apart by something invisible, something silent, something that no one had ever before suspected might exist. The teams checked their results. They checked again. They sent the data to colleagues. They watched for errors. They tested every assumption. And the answer kept coming back the same. The universe is accelerating. There is something in the cosmos that is pushing it apart faster and faster, and we do not know what it is. In 2011, the leaders of those two teams were awarded the Nobel Prize in Physics, not for explaining what they had found, just for finding it. Because what they had found was so unsettling, so unexpected, so foundational to our understanding of the universe, that simply pointing at it deserved one of the highest honors in science. The mystery itself was the achievement. The answer remained, and remains, unknown. Physicists needed a name for this hidden pushing force. They chose a careful, modest, almost humble name. They called it dark energy. The word dark here does not mean evil. It does not mean threatening. It does not mean malicious in any way. It simply means hidden. Dark in the same way a room is dark when you cannot see what is inside it. Dark in the same way a sealed envelope is dark before you open it. Dark because we know it is there, and we know what it does, but we do not yet know what it is. This is important. We are about to spend the rest of this chapter walking through the leading explanations and the staggering implications. But I want you to hold this in your mind first. Dark energy is a placeholder. It is not a finished theory. It is not a confident pronouncement about the nature of reality. It is a name physicists have given to a phenomenon they have observed and cannot fully explain. They are honest about this. They write papers acknowledging it. They tell their students that the leading candidates for what dark energy might be are still candidates, not conclusions. We are looking at one of the largest open questions in modern science, and the honest answer is that no one yet knows what is really happening. But there is a leading candidate, and the leading candidate brings us gently back to the heart of our story tonight. Because the most natural explanation for dark energy, the one that fits best with everything we have already learned about empty space, is that dark energy is the energy of the vacuum itself. Stay with that for a moment. Remember the trembling foam we visited 2 chapters ago. Remember that every cubic centimeter of so-called empty space hums with quantum activity, pairs of virtual particles flickering into existence and vanishing again. Energy appearing and disappearing in a ceaseless storm of microscopic fluctuation. The vacuum is not still. The vacuum has energy. Even at its lowest possible state, the vacuum carries a kind of constant low background of activity that physicists have measured directly with experiments like the Casimir effect. Now imagine that this vacuum energy does something more than just tremble. Imagine that it also pushes. Imagine that every cubic meter of empty space carries within it a tiny, almost imperceptible outward pressure. A faint cosmic exhalation, a gentle insistence on growing. For a single cubic meter, the pressure would be unimaginably small, far too small to detect with any local instrument. You could not feel it. You could not measure it in your kitchen. It would not affect anything in the room around you in any way you could notice. It is so faint, so quiet, so close to nothing, that it took the most distant observations of supernovae across billions of light years before anyone could see its effects at all. But here is the thing about the universe. The universe is large, very large, unimaginably large. And when you have a tiny push in every cubic meter, and then you multiply that push by the staggering number of cubic meters that fill the cosmos, the total becomes enormous. Each tiny push adds to every other tiny push. Each cubic meter of vacuum contributes its small share. And across the vast volume of the entire universe, those small contributions add up to a force that is, right now, in this quiet moment as you rest and breathe, tearing galaxies apart from one another at speeds that increase every year. Picture it gently. The dark space between two distant galaxies, the light from one of them traveling slowly through that dark space on its way toward the other. The space itself, the so-called emptiness between the galaxies, is not just sitting there, it is growing. Each cubic meter of vacuum is, in a sense, asking for a little more room. Each cubic meter is pushing outward, demanding more space, expanding gently. And because there are unimaginably many cubic meters between the two galaxies, the cumulative effect of all that quiet pushing is enough to drag the galaxies apart from one another faster and faster as time goes by. This is what astronomers were seeing in their supernova data in 1998. They were not seeing matter being pushed. They were seeing the space between matter being inflated. They were watching the vacuum reveal itself as not only full of activity, but also full of pressure, full of expansion, full of a kind of cosmic restlessness that does not just sit beneath the visible universe, but actively shapes how the visible universe behaves. Take a slow breath. Settle a little deeper. The picture we are building is strange, but it does not have to feel frightening. The universe expanding, the galaxies drifting, the vacuum pushing, none of this changes the warm room you are resting in tonight. None of this changes the comfort of your blanket or the softness of your pillow. The cosmic forces we are describing are gentle at small scales and overwhelming only at the largest. Your body, your home, your planet, even the solar system itself, are held together by gravity and chemistry far too tightly to be torn apart by the slow push of vacuum energy. The dark energy does its work on the largest possible canvases. It is not coming for your tea. It is only, patiently, slowly, separating galaxies from each other across distances that the human mind can hardly hold. But the implication of all this is what I want you to sit with. The implication is what makes this chapter the most counterintuitive part of our story. Because once you accept that the vacuum carries energy, and that this energy is pushing the universe apart, you have to start asking how much of it there is. How much of this hidden vacuum energy fills the cosmos? And the answer, when astronomers finally worked it out, is staggering. Look at the universe. Look at everything that exists. Every star in every galaxy. Every planet around every star. Every moon, every comet, every asteroid, every cloud of interstellar gas, every nebula, every clump of dust, every speck of cosmic matter you can imagine. All of it. Every visible piece of the cosmos that we have ever detected or photographed or studied. Add it all together. How much of the universe does it make up? The answer is about 5%. 5, not 50, not 80, 5. Everything you have ever seen, every star and planet and lump of rock and beating heart, makes up only about 5% of the total energy content of the universe. The rest is invisible, the rest does not shine, the rest does not interact with light at all in any direct way. The rest is composed of things we cannot see and only partially understand. Of that hidden 95%, about a quarter is something called dark matter. Dark matter is a separate puzzle, related but distinct from dark energy. It is some kind of substance that has weight, that exerts gravity, that holds galaxies together, but that does not give off light or interact with ordinary matter in the usual ways. We know dark matter is there because we can see its gravitational effects on galaxies and clusters, but we do not know what it is made of. That is its own story, for another night. But the remaining 70%, the largest single ingredient in the entire universe, is dark energy, the hidden vacuum push, the cosmic pressure that pulls the galaxies apart. 7 out of every 10 units of energy in the entire cosmos, by the best measurements we have, is the energy of so-called empty space itself. Read that again, slowly, if you need to. 70% of the universe is the energy of the void. 70% of what exists is the activity of the seemingly empty spaces between things. The stars, the planets, the galaxies, the entire glittering visible cosmos that humans have spent thousands of years trying to map is a thin film, a surface, a small 5% crust floating on top of an ocean of vacuum energy that makes up most of everything. Picture it like this. Imagine the universe as an ocean, a vast, dark ocean stretching to every horizon. The ocean itself is dark energy, filling everything, dominating everything, pushing outward in every direction. Now imagine that on top of this ocean, here and there, floating quietly on the surface, there are flecks of foam, tiny bright specks. Each speck is a galaxy. Each speck contains billions of stars. Each star may hold planets. And on some of those planets, there may be living things looking up at the sky and wondering about the ocean they have never directly seen. You are one of those living things. The Earth is a planet around one of those stars. The Milky Way is one of those flecks of foam. Every star you have ever seen in the night sky is part of the same small fleck. Every other galaxy you have ever seen in a photograph is another fleck, drifting alone or in small clusters across the surface of an ocean that we have only just learned exists. The foam is dazzling. The foam is beautiful. The foam contains everything you have ever loved, but it is not the substance of the universe. It is the thin, glittering film on top of something much larger. And the something much larger is the slow, patient, dominant ocean of vacuum energy, the very thing we used to think of as nothing. Let that sit. Take a slow breath. Notice the gentle weight of your body. Notice the soft fabric beneath you. The room around you is small and finite. The cosmos is vast and mostly invisible. And the part of the cosmos you can see, the part that has filled human imagination since the first ancestors looked up from the savannah, is the smaller part, the minor partner, the decoration on top of the actual substance. Now let us bring this down to a scale you can hold in your imagination. Try this. Hold up your hand and pinch a tiny bit of air between your thumb and forefinger. Imagine that small, invisible cube of space between your fingertips, that little pocket of seemingly empty air. Inside that pocket, the same dark energy that fills the cosmos is present. The push is tiny, far too tiny to feel, so tiny that it would take a vast cosmic volume before it added up to anything you could measure. But it is there. The same thing that is pushing the most distant galaxies apart from each other is, in its faintest, quietest way, also present between your fingertips. The largest scale phenomenon in the universe is touching your hand right now. The thing that controls the long-term destiny of galaxies is inside the small space between your fingers. And the same thing fills every other cubic centimeter of the universe, equally, smoothly, without preference. The vacuum energy is not concentrated somewhere far away. It is everywhere. It is in your bedroom. It is in your bones. It is in the gap between your eye and the page of any book you have ever read. The picture this paints is one of the strangest reframings of reality that science has ever produced. We grew up thinking of the cosmos as a great theater. The stage was empty space. The actors were the planets and stars and galaxies. The drama was what happened to the actors. Empty space was the backdrop. Empty space was the floor. Empty space was the place where nothing of importance happened, where things merely sat or moved or interacted, but where space itself had no role to play. Modern physics has slowly inverted this picture. The space is not the backdrop. The space is the main character. The space contains 70% of the energy of the universe. The space shapes the destiny of the cosmos. The actors, the stars and planets and galaxies are the supporting cast. The empty stage was never empty. The empty stage was always doing more than anyone in the audience realized. And the picture gets even stranger when you think about the future. If dark energy continues to push the universe apart at its current rate, or even faster, then the long-term fate of the cosmos is one of slow separation. Galaxies that are not gravitationally bound to each other will drift further and further apart. The light from the most distant galaxies will become harder and harder to see, redshifted into invisibility by the expansion of the space between us and them. Eventually, on timescales of trillions of years, every galaxy outside our local group will pass beyond the cosmic horizon. The night sky will grow gradually emptier. The visible universe will become smaller and smaller, isolated and alone, while the ocean of vacuum energy continues to push everything else further and further away. This is the long-term picture. But it does not have to be a sad one. It is simply a picture, a description of what physics tells us about the largest scales of time. For you, tonight, none of this changes anything. The galaxies are not separating fast enough to matter in any human lifespan. The cosmic horizon is not receding fast enough to take away any star you have ever seen. The sun will continue to rise. The moon will continue to circle the earth. Your room will continue to hold its quiet warmth. The story of dark energy is a cosmic story, a story about the destiny of structures so large that they are barely visible at all from the comfortable scale of our daily lives. But the philosophical implication is the part I want you to carry into the final chapter of our journey tonight. We started this story believing that empty space was simply absence, simply a gap, simply the place where nothing was happening. We have now arrived at a picture in which empty space is the most abundant ingredient in everything that exists. 70% of the universe is the thing we used to call nothing. The vast majority of all the energy in the cosmos is the energy of the void. Stars and planets and galaxies are a minority. The void is the majority. The void is the substance of reality. The visible world is the exception. Sit with that gently. Do not let it frighten you. There is no threat in this picture. The cosmos is not collapsing. The earth is not in any new danger. The story we are telling is simply a description of what is, of what has always been, of what physicists have slowly come to understand over the last several decades. The discovery does not change the world. The discovery only changes our picture of it. The world has always been mostly void. We are only now learning to see it that way. And there is something almost beautiful in this, something that has been waiting for us at the end of this part of our journey. If the void is the substance of the universe, then the visible things, the stars and planets and bodies, are precious in a way they were not before. They are rare. They are local. They are small clusters of organized structure in a much vaster sea of unstructured energy. Every star is a miracle of organization. Every galaxy is a tiny island in a cosmic ocean. Every body, every cell, every heartbeat, is a delicate exception to the general rule of empty space. You are an exception. You are an organized pattern in a universe that is mostly unorganized vacuum energy. The fact that you exist at all, with hands and eyes and a quiet mind that can wonder about the cosmos, is one of the rarer phenomena in the universe. The void is the majority. You are the minority. And the minority is what gets to do the wondering. Take a slow breath. Notice the air entering your lungs. Notice the soft warmth of your body. Notice the quiet pressure of the world around you, gentle and steady, holding you up. You are sitting inside an ocean of vacuum energy that fills the universe and dominates its destiny. You are made of fields that fill every region of space. You are weighed by a syrup that stretches across every galaxy. You are trembled by a foam that hums beneath every layer of reality, and you are pushed gently, ceaselessly, by the same dark energy that is, even now, slowly separating galaxies from one another in the deep darkness of space. You are not separate from any of this. You are not floating on top of it. You are made of it. You are woven from it. Every cell of you carries the same vacuum that fills the cosmos. Every breath you take is full of the same trembling fields. Every heartbeat is in some small way an event in the same fabric that shapes the destiny of all things. In the next part of our journey, we will collapse the cosmic scale back down to the most intimate scale of all. We will return to your own body, to your own breath, to the simple, quiet experience of resting in a room at night. We will ask what it means that the so-called nothing inside you is the same nothing that fills the universe. We will ask what it feels like, gently, to know that you are not solid in the way you used to think, that you are mostly void, that the void is mostly something, and that the something is the deepest fabric of reality. For now, rest with this picture. The void is not empty. The void is not passive. The void is not a backdrop. The void is the majority of everything that exists. And every visible thing you have ever loved, every star, every face, every cup of tea cooling beside a quiet bed, is a small bright pattern on top of an ocean we have only just begun to see. The cosmos is enormous. The void is enormous. And somehow, quietly, you are here, listening, breathing, made of the same fabric as the dark energy that is, even now, gently pushing the farthest galaxies into the unimaginable distance of cosmic time. Let us come home now. We have been traveling for a long time tonight. We have walked through the gardens of ancient philosophers and the candlelit laboratories of 17th century gentlemen. We have stood at the edge of Faraday's iron filings and watched the invisible oceans of fields reveal themselves through patterns in metal dust. We have descended into the trembling foam at the smallest scales of reality. We have learned the name of the syrup that gives every particle its weight. We have looked out at the cosmos and discovered that most of what exists is the energy of so-called empty space itself, an ocean of vacuum pushing galaxies apart across distances the human mind can hardly hold. It has been a long journey, the kind of journey that asks you to keep stretching, to keep reframing, to keep accepting that the picture of the world you carry inside you is a small, partial drawing of something much larger and stranger than your senses have ever shown you. Now let us slow down. Let the cosmic scale fold gently back inward. Let the galaxies drift quietly into the background. Let the trembling fields hum softly somewhere just beyond your awareness. And let us bring everything we have learned down to the simplest, closest, most intimate scale there is. Your own body. You are lying somewhere. A bed, a couch, a quiet room with the light low. Your eyes may be closed or half closed. Your breath is slow. Your shoulders, perhaps, are finally beginning to soften after the long day that brought you here. You feel, more than anything else, solid. You feel the steady pressure of your back against the surface beneath you. You feel the gentle weight of the blanket. You feel the boundary of your skin, the edge where you end and the rest of the world begins. This is the most familiar feeling in the world. It is the feeling of being a body, of being a self, of being a thing. Stay with that feeling. Do not try to change it. It is real in every way that matters to a human life. But hold it gently, because tonight, having walked through the long story of what fills the void, we are going to look at this feeling in a slightly different way. Not to take it from you, not to make you doubt the comfort of your own form, only to widen what it means. You are made of cells, many, many cells, tens of trillions of them, woven together into the patterns of your tissues and organs and bones. Your heart is a cluster of cells. Your lungs are a cluster of cells. Your skin is a cluster of cells. Each of those cells is itself made of countless smaller pieces, the molecules and proteins and structures that allow it to do its work of being alive. But cells are not the smallest layer of you. Cells are made of molecules. Molecules are made of atoms. And atoms, when you finally arrive at them, turn out to be something rather different from what they look like in the diagrams of a school textbook. Picture a single atom inside the tip of your finger. The diagrams you grew up with probably showed it as a small, dense ball with smaller balls orbiting around it, like a tiny solar system. That picture is not entirely wrong. There is a nucleus at the center. There are electrons surrounding it. But the picture leaves out the most important thing. The diagrams are not drawn to scale. If you took a single atom inside your fingertip and blew it up to the size of a large cathedral, the nucleus at its center would be about the size of a grain of rice. A single grain of rice sitting in the middle of an empty cathedral. The electrons would be smaller still, almost vanishingly small, drifting somewhere within the vast hollow space of the cathedral walls. Almost everything inside the atom is, by any ordinary definition of the word, empty. Now, apply that picture to your finger. Your finger is not a solid piece of matter. Your finger is mostly the same kind of inside the atom emptiness that fills the cathedral around the grain of rice. Your bones are the same. Your muscles are the same. Your eyes, your tongue, your brain, every part of you that you have ever touched or seen or known is overwhelmingly composed of the spaces between particles rather than the particles themselves. If you could somehow remove all the empty space from every atom in your body, if you could collapse every cathedral down so that only the grains of rice remained, the entire mass of you would shrink down to something smaller than a single speck of dust. Everything else, every visible part of your body, every familiar contour of your form, is shape, not substance. It is pattern, not matter. The fullness of you, as you have always experienced it, is in some real and physical sense an illusion of patterns stretched across an enormous amount of so-called emptiness. But of course, tonight, we have learned something important about that emptiness. We have learned that the so-called empty space inside an atom is not empty at all. We have learned that the gap between the grain of rice and the cathedral walls is filled with the same things that fill the gap between the Earth and the farthest star. It is filled with the electromagnetic field, shimmering quietly with the possibility of light. It is filled with the gravitational field, gently shaping the geometry of space itself. It is filled with the strong and weak nuclear fields, doing their quiet work at scales smaller than any microscope can ever resolve. It is filled with the trembling foam of the quantum vacuum, with virtual particles flickering into existence and vanishing again at rates no clock could ever measure. It is filled with the syrup of the Higgs field, the very thing that gives your particles the property we call weight. And it is filled with the silent push of dark energy, the vacuum pressure that, in its tiny way, is even now contributing to the slow expansion of the cosmos. The space inside your atoms is the same space that fills the universe. Let that sentence settle. Take a slow breath if it helps. The fields and foam and pressure that we have spent the last several chapters describing are not somewhere far away. They are not concentrated in distant nebulae or strange laboratory experiments. They are inside you. They are inside every cell of your body. They are inside every cathedral of every atom in your skin. The void we have been exploring all night is the same void that makes up most of your body. You are not separate from it. You are made of it. Stay with that for a few breaths. Notice how, even now, hearing this, the feeling of solidity does not vanish. The blanket still rests on your chest. The pillow still cradles your head. Your hands still feel like hands. The picture has changed, but the experience has not. And that is one of the gentle beauties of this idea. The strangeness of physics does not undo the comfort of being a body. It only adds a quieter, deeper layer underneath. Solidity remains as a feeling. The fullness underneath the solidity is what we have been learning to see. What does it mean to be solid when solidity, at the deepest level, is an illusion? This is one of those questions that can be answered 1,000 different ways, and none of them entirely complete. But here is one gentle answer. Solidity is real as an experience. Solidity is the way certain kinds of patterns interact with other kinds of patterns. When your hand presses on the blanket, the electrons in your skin push against the electrons in the fabric, and the field between them carries that push back to your senses as the feeling of contact. The blanket is mostly empty. Your hand is mostly empty. But the patterns of energy that we call hand and blanket interact in ways that feel reliable, that feel substantial, that feel solid to a being made of similar patterns. The experience is true. The picture beneath the experience is simply richer than the experience suggests. You can hold both at once. The blanket is solid. The blanket is mostly void. Both statements are true. They live at different scales. They do not cancel each other. They simply add depth to what was once a flat picture. And what does it mean to be alone when the field that gives you weight stretches across every galaxy? This is another question worth sitting with gently. We often think of ourselves as isolated, a self enclosed inside a body, looking out through the windows of two eyes, separated from everything else by the boundary of the skin. The loneliness that visits people sometimes in the quiet hours of the night is often built on this picture. The picture of being a small, isolated thing inside a vast, indifferent space. But tonight, we have walked through a story that complicates that picture. The Higgs field that gives every cell of your body its mass does not begin at your skin and end somewhere on the other side of it. It stretches outward. It fills the room. It fills the city. It fills the country. It fills the planet. It fills the solar system. It fills the galaxy. It fills every cubic centimeter of every region of space in the entire observable universe. The same field that makes your hand heavy enough to rest on the blanket is the field that makes distant stars heavy enough to burn. The same field that gives you a body is giving everybody in every galaxy, in every cluster, of every supercluster, across all the cosmos, a body as well. You are connected to everything through a field you cannot see. The substance of your weight is the same substance as the weight of every star. The cosmic medium that makes you possible does not stop at your skin. It does not even slow down at your skin. It passes through you the way it passes through everything, present at every point, present at every scale, present in every region. If aloneness means being made of materials that exist only inside your own boundaries, then in that sense, you have never been alone. The materials that compose you are everywhere. The fields that hold you together stretch across the universe. The vacuum that hums inside your atoms is the same vacuum that hums between the most distant galaxies. By the standards of physics, you are continuous with the cosmos in a way no philosophy or religion ever quite managed to put into words. This does not erase loneliness as a human experience. Loneliness is real. Loneliness has its own weight and its own meaning. But it is worth knowing, especially in the quiet hours of the night, that the picture of yourself as a small, isolated thing in an empty space is a partial picture. The deeper picture is that you are woven through with everything. The fields do not abandon you when you feel alone. The void does not become any less full when no one is talking to you. The trembling foam inside your bones is the trembling foam of the universe. You are not separate from the cosmos. You are one of its patterns. You are one of its expressions. You are one of the ways the cosmic fabric has folded itself into a shape that can wonder about the fabric. And what does it mean to call anything empty when emptiness is the most crowded thing in existence? This may be the gentlest reframing of all. We have spent so much of human history using the word empty to mean nothing. An empty room means a room with no people in it. An empty box means a box with no objects inside. An empty stomach means a stomach without food. The word has always carried with it the implication of absence, of lack, of waiting to be filled by something more interesting. But after tonight, we know that physical emptiness is the opposite of absence. The empty room is full of air, full of fields, full of trembling foam, full of vacuum energy, full of the same dark energy that fills the cosmos. The empty box is also full of all those things. The empty stomach, the empty cup, the empty hand, the empty sky are all full of fields and foam and force. Emptiness, in the physical sense, is the most crowded thing in existence. It is the most active. It is the most abundant. It is the deepest layer of reality that we have so far been able to point at. It is the thing that makes everything else possible, and it is everywhere. There is no part of the universe that is not full of it. There is no corner of your body that is not full of it. There is nothing that has ever been called empty that was not, in fact, brimming with more substance than the words of any language have ever been able to capture. Sit with that. Let the language slow down inside you. The empty space around your hand, the empty space inside your chest, the empty space between the words you are hearing. None of it is empty. All of it is alive. All of it is full. The very fact of being able to call something empty was always, in some deep sense, a misunderstanding, a useful one for daily life, but a misunderstanding nonetheless. Let yourself breathe slowly here. There is no need to rush. The story is almost finished. The walk is coming to its end. What remains is to settle into the gentle resting place that all this knowledge offers, if you let it. Notice the air around your body. The room you are lying in is full of it. Soft, quiet, gentle air. Air that carries the breath of everything that has ever lived nearby. Air that has passed through countless other lungs and leaves and forests and oceans before drifting in here and finding its way to your own slow breathing. That air is itself full of fields, full of trembling, full of the same vacuum energy that fills the cosmos. The room around you is not surrounded by emptiness. It is surrounded by fullness. It is held in fullness. It is woven from fullness all the way out to the farthest stars. Notice the gentle hum of the world, not the noises of the room, but the quieter underlying presence that comes when noises fade. Even in the most silent moment of the most silent night, the universe is humming. The fields are humming. The foam is trembling. The vacuum energy is pushing, ever so softly, in every direction at once. You cannot hear it with your ears. You cannot feel it with your skin. But you can know it is there, and you can rest inside it. the way a small bird rests inside the wide, quiet branches of a sleeping tree. Notice the space you occupy, the shape of your body laid out beneath the blanket, the pillow under your head, the room around your form, with its walls and ceiling and door. All of that space, every cubic centimeter of it, is filled with the same fabric that fills the cosmos. You are not floating in a void. You are floating in a fullness so deep that no language has ever fully named it. The fabric of reality is cradling you tonight. It has always been cradling you. It has cradled every night of your life, even the ones you do not remember. You have never, for a single instant, been outside of it. Let your shoulders soften. Let your jaw relax. Let your hands rest open. The fullness is here. The fullness is in your chest, in your breath, in the warmth of your skin. The fullness is in the air above you, in the floor beneath the bed, in the walls of the building, in the soil under the building, in the sky above the building, in the dark spaces between the stars. The fullness is continuous. There are no seams. There are no gaps. There is no place where the fabric ends and a true emptiness begins. The fabric reaches everywhere. The fabric is everywhere, and you are woven through it like a single thread in an unimaginably vast tapestry. The universe began long before you. It will continue long after you. But for this moment, this single quiet moment, in the long unfolding of cosmic time, you are here, you are listening, you are breathing. You are a pattern of fields and foam, organized into a shape complex enough to wonder about the fields and the foam. You are the universe folded into a place that can know itself, even if only briefly, even if only partly, even if only with the gentle, imperfect light of human understanding. Rest in that knowledge tonight, not as a fact you need to remember, not as an answer you need to hold on to, simply as a quiet feeling, a widening of the small word self into something larger, a softening of the boundary between body and world, a recognition that the so-called nothing around you is the deepest something that has ever been described, and that you are made of the same something, and that the something has never, not once, not for a single instant, abandoned you. Let your breathing slow. Let the day soften. Let the worries of the daylight world begin to drift away, the way mist drifts off a pond as the sun begins to set. The cosmos is enormous. The cosmos is full. The cosmos is reaching gently into every cell of your body and holding you. You are cradled by the void that turned out not to be a void. You are cradled by the fullness that fills the universe. The chamber was not empty. The fields were not still. The foam was not silent. The syrup was not absent. The pressure was not nothing. And the space around you tonight, the room with its quiet walls, the bed with its soft covers, the air that carries your slow, careful breath, is not the absence of anything. It is the presence of everything we have spent this long evening learning to see. You are not alone. You are not adrift. You are not a small thing in a large, indifferent emptiness. You are a wave on the surface of an ocean that has no shore. You are a pattern in a fabric that has no end. You are a knot in a field that holds every star together. You are a soft, trembling shape inside the deepest fullness the universe contains. Let sleep find you, gently, whenever it is ready. Let your eyes close fully if they have not already. Let the slow, ancient rhythm of your breath carry you down into the rest you deserve. Tomorrow the world will be there. The light will return. The familiar shapes of life will reassemble around you. And underneath all of it, quietly, patiently, the fullness will still be present, just as it has always been, holding the room and your body and the planet and the stars and the long invisible weave of everything that exists. The void was never empty. It was always full, and so are you. Rest now. The fields will keep singing while you sleep. The foam will keep trembling. The fullness will keep cradling you. There is nothing you need to hold. There is nothing you need to do. The universe has been holding you all along, and it will not stop tonight. Close your eyes. Let go. Drift gently into the fullness. You are home.